guys, it's Nem and welcome to my Physics 2111 lab. So this lab, the purpose of my experiment is going to be observing the motion of an object which is dropped from rest, and it's going to end up displaying characteristics of drag because final velocity and initial velocity are not going to be the same. And then we're going to look at how drag force affects predicted gravity by looking at a computer generated just gravity graph and then one of drag and gravity and see how they differ. And then a little bit of results is that the graph with both gravity and drag ended up being more similar and accurate to the actual results than the graph with only gravity. And so here are some of the physics principles and scientific backgrounds. So the first thing we need to look at is Newton's second law. So like I said, v final and v initial are not going to be the same. And since velocity is not constant, I thought it would be better to use the v final equation instead of just F net equals ma. And so this equation, velocity initial is going to be 0 meters per second, the mass is going to be 4 kilograms, and delta t is going to be 0.035 seconds. And then we're going to look at a little bit about how F net is actually negative instead of just being 0 and constant like the lab from last week. Then also the gravitational force, which is the force pointing downwards in this example. So this equation is negative mg times j hat. So j hat is the direction of the force, which in this case only changes on the y-axis, and it is going downward. And then it's also m equals mass, and then g is obviously the acceleration on an object due to gravity, which we know is 9.8. And then now moving on to the drag force. So the first we need to look at this equation is negative b, which is the proportionality constant. And this constant doesn't have an exact value because as you're looking at different objects, they have different shapes. So like the drag of an airplane and the drag of like a feather or a balloon or maybe like a plate are going to be totally different just because of the different sizes which they contain. And then again, we have velocity vector and v hat, which is the direction. And then we also have Newton's third law, which states that the gravity force and drag force are going to be exactly opposite because an action is going to have an equivalent opposite reaction. And then the initial conditions of this experiment is that the initial velocity is going to be 0, 0, 0 because it's not moving, it's being dropped. And then our initial time is 0. And then how I set it up on Tracker was that the original position from where the hat starts is going to be at 0, 0, 0 axes. So the system of this experiment is going to be my buzz hat, which I'm going to drop, and then the surroundings are the atmosphere and air resistance, the earth, and my hands, which are being used to drop it. So here's a video of that happening.
There we go.
So as you can see, the top right and the bottom left graph are going to be the ones which I used coding to make, and they're like perfect graphs. And then the top left is the actual graph, which I got from Tracker, and I used the auto tracker to just click on the hat every single second or frame. And then the bottom right, as you can see, the graph that had gravity and drag, which is the green line, is a lot closer to the actual red line. And that means that there had to be drag here because the gravity line is a lot far off from the actual, so there had to be some kind of other component, which is drag. And then, so this is the free body diagram which I made in order to display this. So as you can see on the left side, Fg is actually longer than F drag, which means that the forces are not equal, and F net is going to be going in a negative y direction because Fg is bigger than F drag. So you have big negative plus a smaller positive. So as you can see, the vector is going to be negative on the y-axis. And then here's the coding, which the only difference between them is going to be the proportionality constant for drag and then also the equations. So on the left, gravity coding, it's just F net is equal to weight, which is the negative mass of the ball times j hat times g. Then on the right, you also had to include the drag force, which is negative b times the magnitude of the velocity squared times negative j hat. And then some errors in this example were that it was actually raining and really windy when I did this experiment. So the hat didn't fall directly down, it actually fell a little bit sideways. So it had to incorporate the x-axis, but just because of the way that this experiment set up, I didn't end up including it just because it was not very important to the results. And then some what ifs are about the terminal velocity. So in the original graphs, the terminal velocity would have never been reached because FD never equals FG because it just kind of like goes like this. However, when we incorporate like throwing it down instead of dropping it, the hat actually, with the gravity and drag, does a very like sudden and then kind of drops off. So the asymptote goes on forever, which means that at some point the linear graph of gravity does have to hit it. And so, yes, there is a terminal velocity when it drops to the ground. Thank you so much for watching. Have a great day. Goodbye.